Welcome to today's discussion on the captivating subject of zero-point energy and the feasibility of a zero-point power module, or, for Stargate fans, a ZPM. In a world striving for sustainable and abundant sources of energy, the concept of zero-point energy holds tremendous intrigue and potential. Today, we'll delve into the fundamental principles behind zero-point energy and explore its implications for our understanding of the universe, and examine the current state of research on harnessing this enigmatic energy source. Howdy, I'm just some random nude dude sitting in my closet talking to myself. It's also where I celebrate the power of free thinking and encourage bold ideas. As a society, we're often afraid to challenge the norms and think outside the box. But here, I embrace the unconventional. So sit back, relax, and join me on this journey of exploration where we embrace our inner nude dude and push boundaries to discover new perspectives. Zero-point energy emerges from the principles of quantum mechanics, challenging our traditional notions of empty space. At the core of this concept lies the fascinating idea of inherent uncertainty in nature. According to the Heisenberg uncertainty principle, it's impossible to simultaneously know the exact position and momentum of a particle with absolute certainty. This uncertainty gives rise to fluctuations in energy, even in a system at its lowest possible energy state, known as the ground state. Zero-point energy refers to the residual energy that remains in a physical system, even at a temperature of absolute zero, 0 degrees Kelvin, or minus 459 degrees Fahrenheit for those of you in America, or minus 273 degrees Celsius for everyone else on the planet. It's the energy that persists when all other forms of energy have been removed. In this state, particles are as close to a state of rest as they can be, yet still possess energy due to the inherent fluctuations dictated by quantum mechanics. This concept challenges our conventional understanding of empty space, revealing a dynamic and lively energy field that pervades even seemingly empty regions. Quantum field theory describes these fluctuations as vacuum fluctuations, fundamental to the fabric of the universe. These fluctuations give rise to the constant motion and interaction of particles, fields, and forces. Zero-point energy exists everywhere, pervading even the emptiest of spaces. It serves as a reference point, the baseline energy level from which all other energy states are measured. The potential of zero-point energy as a limitless energy source has captivated the scientific community for decades. It holds the promise of a paradigm shift in energy generation, offering the possibility of abundant, sustainable power that could revolutionize our technological capabilities. However, realizing this potential poses significant challenges and limitations. In this discussion, we'll explore the current understanding of zero-point energy, examine experimental devices and prototypes developed to harness this energy, and discuss the limitations and feasibility of a practical zero-point power module. While the journey towards practical zero-point energy utilization is ongoing, it is through rigorous scientific exploration, technological advancements, and interdisciplinary collaboration that we inch closer to unlocking the true potential of this cosmic energy source. So join me as we delve into this fascinating world of zero-point energy and explore its implications for our future energy landscape. Let's embark on a journey of discovery and imagination as we strive to uncover the mysteries of this captivating energy phenomenon. Zero-point energy is a mind-boggling concept that emerges from the principles of quantum mechanics. At the heart of this concept lies the fundamental uncertainty inherent in nature. According to the Heisenberg uncertainty principle, it is impossible to know both the exact position and momentum of a particle simultaneously with absolute certainty. This uncertainty gives rise to fluctuations in energy, even in a system at its lowest possible energy state, which is known as the ground state. Zero-point energy is the residual energy that remains in a physical system, even at a temperature of absolute zero. In this state, particles are as close to a state of rest as they can be, yet still possess energy due to the inherent fluctuations. It's as if the fabric of space itself is teeming with energy, with particles popping in and out of existence in a perpetual dance. Quantum field theory describes these fluctuations in energy as vacuum fluctuations. They are not merely random fluctuations. Instead, they are fundamental to the fabric of the universe. Every particle, every field, and every interaction is influenced by these fluctuations. This energy exists everywhere, pervading even the emptiest of spaces. The term zero point arrives from the fact that this energy is the lowest possible energy that a quantum system can possess. It serves as a reference point, a baseline from which all other states are measured. Even when all other energy is removed from a system, zero-point energy remains, defining the system's minimum energy level. This concept challenges our traditional understanding of empty space. It reveals that even in seemingly empty regions, the vacuum is teeming with a dynamic and fluctuating energy field. Although we cannot directly access or manipulate this energy with our current technology, its existence has profound implications for our understanding of the universe and our quest for new sources of energy. Understanding and harvesting zero-point energy offers tantalizing prospects for limitless energy generation. However, the practical utilization of this energy is a complex challenge that requires overcoming the limitations imposed by quantum mechanics and thermodynamics. While scientists and researchers have made progress in exploring and experimenting with zero-point energy, we are still far from realizing its full potential as a practical energy source. The concept of harnessing zero-point energy has captivated scientists and researchers for decades. Its potential as an abundant and sustainable energy source has sparked a quest to unlock its secrets and develop practical applications. While significant challenges exist, the pursuit of harnessing zero-point energy holds the promise of a paradigm shift in energy generation. One of the main challenges lies in extracting and converting the energy from the quantum vacuum efficiently. The energy density of zero-point energy is incredibly low, making it difficult to capture and utilize in a practical manner. It requires advanced technologies capable of extracting and amplifying this energy while minimizing losses and maximizing efficiency. Various approaches have been explored to harness zero-point energy. One method involves utilizing the Casimir effect, which arises from the interaction between fluctuating electromagnetic fields and boundaries. The Casimir effect creates a measurable force between closely spaced conductive plates, indicating the presence of zero-point energy. Researchers have investigated using the effect to extract useful energy, although significant engineering hurdles remain. Another avenue of exploration focuses on manipulating quantum fields to tap into zero-point energy. Quantum field theory provides a framework for understanding the behavior and interactions of these fields. Scientists have proposed using a quantum mechanical system, such as nanoscale oscillators, not to be confused with oscillation overthrusters, or superconducting circuits to couple with and extract energy from the underlying quantum vacuum. Additionally, advancements in nanotechnology and metamaterials hold potential for harvesting zero-point energy. Manipulating the properties of materials at the nanoscale may enable the design of structures that can efficiently capture and convert the energy from vacuum fluctuations. It's important to emphasize that practical devices capable of harnessing zero-point energy on a large scale have not yet been realized. The current state of research and development primarily focuses on proof-of-concept experiments and small-scale prototypes. Scientists continue to grapple with the technological and theoretical challenges associated with extracting and utilizing this energy source efficiently. Moreover, there are still scientific debates and discussions regarding the feasibility and viability of a zero-point power module. Skeptics point to the significant technological and engineering obstacles that must be overcome, as well as the potential limitations imposed by fundamental physical laws. Nonetheless, the quest for harnessing zero-point energy remains an active and exciting area of research. It pushes the boundaries of our scientific understanding and fuels innovation for the pursuit of cleaner, more sustainable energy sources. Continued exploration and advancement in areas such as quantum technologies, material science, and energy conversion methods hold the potential to bring us closer to the practical realization of zero-point energy as a viable power source. In the quest to harness zero-point energy, scientists and researchers have developed experimental devices and prototypes to explore the characteristics and potential applications of this enigmatic energy source. While these devices are not yet capable of meeting our energy demands, they provide valuable insights and pave the way for future advancements. One area of experimentation involves utilizing nano and microscale devices. These devices take advantage of the unique properties of quantum mechanics to interact with the zero-point energy field. Examples include nanoscale oscillators, microelectric mechanical systems, or MEMS, and superconducting circuits. These devices can resonate at specific frequencies, potentially extracting energy from the vacuum fluctuations. Another approach focuses on utilizing the Casimir effect, which manifests as an attractive force between closely spaced conductive plates due to the zero-point energy. Researchers have conducted experiments to measure and manipulate the Casimir force, with the goal of eventually harnessing it as a source of energy. However, practical implementation and scalability of this approach remain significant challenges. Furthermore, advancements in metamaterials have opened up new possibilities for capturing and manipulating zero-point energy. Metamaterials are engineered materials with unique properties not found in nature. By designing metamaterial structures at the nanoscale, scientists aim to enhance the interaction with zero-point energy and develop efficient energy harvesting systems. It's important to note that these experimental devices and prototypes are still in the early stages of development. They serve as crucial stepping stones towards understanding and harnessing zero-point energy. While their current energy outputs are modest and far from meeting practical energy needs, they provide valuable proof-of-concept demonstrations and contribute to our knowledge base. The exploration of zero-point energy devices is an interdisciplinary endeavor, combining principles from physics, engineering, material sciences, and quantum mechanics. Scientists and engineers around the world collaborate and share their findings to push the boundaries of what is currently possible. As research and technological advancements continue, the focus shifts towards improving device efficiency, minimizing losses, and exploring novel approaches. Scientists are investigating advanced materials, quantum coherence, and novel energy conversion methods to enhance the practicality and scalability of zero-point energy devices. While challenges and limitations remain, these experimental devices and prototypes showcase the dedication and innovation of researchers striving to unlock the potential of zero-point energy. They lay the groundwork for future breakthroughs and bring us one step closer to the realization of a practical zero-point energy module. Zero-point energy holds immense potential for a wide range of applications that could transform various industries and technologies. While the practical implication of a zero-point power module is still a subject of ongoing research and development, the potential benefits of harnessing zero-point energy are worth exploring. So let's delve into some potential applications that could arise from the utilization of zero-point energy and a practical zero-point energy power module. One of the most significant potential applications for zero-point energy lies in sustainable energy generation. If harnessed efficiently, zero-point energy could provide a virtually limitless and clean source of power. A practical zero-point power module could revolutionize the energy landscape, offering a sustainable alternative to traditional fossil fuel-based energy generation. This could contribute to mitigating climate change, reducing carbon emissions, and addressing global energy demands. The utilization of zero-point energy could have groundbreaking implications for space exploration. In the vastness of space, where resources are limited and energy is crucial, a zero-point power module could provide a compact and efficient power source for spacecraft and space stations. The abundance and stability of zero-point energy make it an ideal candidate for powering long-duration missions, enabling greater mobility and supporting advanced scientific research in space. Zero-point energy is intricately connected to the principles of quantum mechanics. Harnessing this energy source could unlock new possibilities in the field of quantum technologies. Quantum computing, quantum communication, and quantum sensing could benefit from the stability and abundance of zero-point energy. A practical zero-point power module could provide the necessary energy to power quantum devices and facilitate advancement in these transformative technologies. The field of nanotechnology could see significant advancements with the availability of abundant zero-point energy. Nanoscale devices, sensors, and electronic systems could benefit from a compact and efficient power source. Zero-point energy could power microelectrical mechanical systems, or MEMS, nanoscale sensors, and nanorobots, enabling a new era of miniaturized, self-sustaining technologies with a wide range of applications in medicine, electronics, and environmental monitoring. Zero-point energy could prove invaluable for remote and autonomous systems that operate in isolated or hard-to-reach locations. These systems, such as remote environmental monitoring stations, deep-sea exploration robots, or space probes, often require long-lasting and self-sustaining power sources. A practical zero-point power module could provide the energy required to power these systems, eliminating the need for frequent maintenance or reliance on external power sources. In humanitarian and disaster relief scenarios, access to reliable power sources is critical to providing essential services, communication, and medical support. Zero-point energy could offer a decentralized and sustainable power solution, enabling quick deployment and operation of critical infrastructure in emergency situations. The abundance and stability of zero-point energy make it a potentially invaluable resource for addressing humanitarian needs and disaster response efforts. These are just a few examples of the potential applications that could emerge from the utilization of zero-point energy and a practical zero-point power module. While these applications are speculative at this stage, they demonstrate the far-reaching impact that harnessing zero-point energy could have on various industries, technologies, and global challenges. It's important to emphasize that the realization of these applications depends on overcoming technological challenges, enhancing energy extraction efficiently, and advancing our understanding of zero-point energy. Continued research, collaboration, and technological advancements will be crucial in unlocking the full potential of zero-point energy and transforming these applications from concepts into tangible realities. As scientists and researchers delve deeper into the exploration of zero-point energy, they encounter significant challenges and limitations that affect the feasibility of a practical zero-point power module. These limitations arise from the fundamental principles of quantum mechanics and thermodynamics, as well as the current state of technology. Understanding these obstacles is crucial for evaluating the viability of harnessing zero-point energy on a large scale. One major limitation is the extremely low energy density of zero-point energy. The energy available in the quantum vacuum is minuscule, making it challenging to extract and convert into usable energy. The low energy density necessitates highly efficient and sensitive methods for capturing and amplifying this energy while minimizing losses. Achieving such efficiency remains a significant technological hurdle. Another challenge is related to the uncertainty principle in quantum mechanics. The uncertainty principle imposes limitations on our ability to precisely measure and manipulate energy in particles at the quantum level. These limitations make it challenging to control and utilize zero-point energy effectively. Developing techniques that overcome these limitations and allow for accurate manipulation of quantum states is a critical area of ongoing research. Thermodynamic considerations also present challenges for the practical utilization of zero-point energy. The second law of thermodynamics states that energy tends to disperse and become less concentrated over time, leading to a decrease in useful energy. Extracting energy from the vacuum and manipulating a high energy concentration presents a significant thermodynamic challenge. Moreover, there are ongoing debates within the scientific community regarding the true nature and magnitude of zero-point energy. Some argue that zero-point energy represents a vast and untapped resource, while others question its potential for practical energy generation. These people are mostly in Texas and other oil-producing areas. These debates underscore the need for rigorous scientific investigation and further technological advancements to clarify the feasibility of a zero-point power module. Additionally, the development of a practical zero-point power module requires advancements in material science, engineering, and energy conversion technologies. Overcoming technical hurdles, such as maximizing energy capture, minimizing losses, and ensuring scalability, is essential for realizing the potential of zero-point energy as a viable energy source. Despite these limitations and challenges, researchers remain committed to exploring the frontiers of zero-point energy. Ongoing scientific investigations, coupled with advancements in quantum technologies, nanomaterials, and energy conversion systems, offer hope for overcoming these hurdles and unlocking the potential of zero-point energy as a sustainable and abundant power source. It's essential to approach the feasibility of a zero-point power module with a balanced perspective. While significant progress has been made in understanding and experimenting with zero-point energy, achieving a practical and scalable energy solution based on this concept requires further breakthroughs and interdisciplinary collaboration. As we contemplate the future of zero-point energy, we find ourselves at the threshold of a transformative energy landscape. While the realization of a practical zero-point energy module capable of meeting our energy needs remains uncertain, the pursuit of zero-point energy continues to inspire scientists, engineers, and innovators worldwide. The journey towards harnessing this vast cosmic energy source holds immense potential for shaping our sustainable future. Advancements in scientific understanding, technological breakthroughs, and collaborative efforts within the research community are paving the way for the future of zero-point energy. Scientists are continuously refining experimental techniques, exploring new materials, and investigating innovative approaches to unlock the true potential of this enigmatic energy source. The ongoing refinement of nanotechnology and metamaterials offers promising avenues for capturing, manipulating, and converting zero-point energy. By tailoring materials at the nanoscale, scientists aim to enhance energy extraction efficiency and develop novel energy harvesting devices. Advancements in material science and engineering will play a vital role in shaping the future of zero-point energy technologies. Furthermore, the emergence of quantum technologies opens up exciting possibilities for harnessing zero-point energy. Quantum computing, quantum sensors, and quantum information processing provide new tools and techniques that can contribute to our understanding of zero-point energy and its practical applications. Collaboration and knowledge sharing among researchers across various disciplines will continue to drive progress in zero-point energy research. The interdisciplinary nature of this field demands the integration of expertise from physics, engineering, material science, and beyond. By fostering collaboration and facilitating the exchange of ideas, scientists can accelerate the pace of innovation and overcome the challenges that lie ahead. The future of zero-point energy also depends on public support, policy initiatives, and investment in research and development. Governments, industry, and organizations need to recognize the potential of zero-point energy as a sustainable and clean power source. By providing funding, resources, and supportive policies, we can create an environment that nurtures groundbreaking research and enables the translation of scientific discoveries into practical applications. While we cannot predict with certainty the timeline for achieving a practical zero-point power module, the continued pursuit of zero-point energy is essential for our long-term energy sustainability. It represents an opportunity to diversify our energy sources, reduce reliance on finite resources, and mitigate environmental impacts. The future of zero-point energy holds tremendous promise and potential. While challenges and uncertainties remain, The relentless efforts of scientists and engineers, coupled with advancements in technology and interdisciplinary collaboration, brings us closer to realizing the practical utilization of zero-point energy. Let's remain optimistic, open-minded, and dedicated to exploring the vast possibilities of zero-point energy, envisioning a future where it plays a vital role in powering our homes, cities, and industries. The exploration of zero-point energy and the feasibility of a zero-point power module represent a captivating and complex scientific journey. While the practical realization of zero-point energy as a reliable energy source is still on the horizon, the pursuit of this enigmatic energy concept has far-reaching implications for our understanding of the universe and our quest for sustainable energy solutions. Zero-point energy challenges our traditional notions of empty space, revealing a dynamic and fluctuating energy field that pervades even the emptiest regions. It embodies the inherent uncertainty and vitality of quantum mechanics, offering a glimpse into the fundamental fabric of our reality. While harnessing zero-point energy poses significant challenges, such as low energy density, limitations imposed by quantum mechanics and thermodynamics, and the need for technological advancements, researchers persist in their endeavors. They push the boundaries of scientific knowledge, explore new materials, and refine experimental techniques to unlock the true potential of zero-point energy. The future of zero-point energy hinges on interdisciplinary collaboration, technological innovation, and supportive policies. Continued collaboration among physicists, engineers, material scientists, and other experts is crucial to unraveling the mysteries of zero-point energy and translating theoretical concepts into practical applications. Public support and investment in research and development are equally vital. By recognizing the potential of zero-point energy as a sustainable and abundant energy source, governments, industries, and organizations can foster an environment conducive to breakthrough discoveries and transformative technologies. While the timeline for a practical zero-point power module remains uncertain, the journey itself holds immense value. It expands our knowledge, inspires innovation, and fuels our imagination. The quest for zero-point energy epitomizes the human spirit of exploration and our relentless pursuit of a better future. Let's remain committed to pushing the boundaries of scientific understanding, embracing curiosity, and nurturing the scientific endeavors that explore the mysteries of zero-point energy. Together, we can shape a future where zero-point energy plays a vital role in addressing our energy needs, mitigating environmental impacts, and propelling us towards a sustainable and prosperous world. Thanks for tuning in. I hope you found this video informative and thought-provoking. This is the point at which others tell you, if you enjoyed it, please give it a thumbs up and consider subscribing to our channel for more content just like this. But we all know that kind of thing is for losers. Don't be a loser. And as always, I welcome your feedback and ideas for future videos in the comments section below. Until next time, keep exploring, keep learning, and keep embracing your inner nude, dude.